students. In last module of unit 3 we discussed about rapidly varying flow. In this module we will know about how to derive a hydraulic jump equation, which is nothing but depth of hydraulic jump equation, and also energy loss or head loss in hydraulic jumps. Okay, before going to that, let's revise what is rapidly varying flow and hydraulic jump, then we'll go for derivation. Okay, we know what is rapidly varying flow. Rapidly varying flow is nothing but if the depth of flow changes rapidly, that means there will be a change within a short length. Within a short length there will be a huge difference in its depth. That is called rapidly varying flow, capital RVF. Then we discussed about its characteristics. First characteristics is its pressure distribution will not be hydrostatic, and there will be losses and eddies, and there will be no friction loss. There will be no friction loss and there will be no shear loss also. Okay. Next, we discussed about difference between gradually varying flow and rapidly varying flow. In gradually varying flow, it occurs over a long distance, but rapidly varying flow, there will be depth variation within a shorter length. Okay. Then in gradually varying flow, friction is a predominant one. We cannot ignore friction. But in rapidly varying flow, we may ignore the friction also. Okay. Then next is we discussed about hydraulic jump. Hydraulic jump derivation is nothing but similar to the rapidly varying flow definition only. There will be an increase in depth within a short length. Okay, that is called hydraulic jump. In this hydraulic jump, when hydraulic jump occurs means in hydraulic jump flow will change from supercritical to subcritical. Flow will change from supercritical to subcritical. Okay, then there will be a loss of energy in hydraulic jump also. Okay, it's an example for hydraulic jump. First, in section 1 there will be flow will be in a supercritical condition. In supercritical condition means there fluid number will be greater than 1. Okay, velocity will be more but depth will be very less at section 1. In there depth is denoted as small d1. That is nothing but depth before jump. After hydraulic jump there will be a section 2. In section 2 depth will be huge comparing to depth at 1. So depth at 2 will be 3 or not 3 or 4 approximately 6 or 7 times greater than depth at 1, and at depth at section 2 flow will be subcritical. So at section 1 flow will be supercritical, at section 2 flow will be subcritical. Okay, so from 1 to 2, from section 1 to 2 there will be a loss of energy, loss of head happens. Okay, why that is happening means we will discuss in later. Okay, then applications of hydraulic jump. First application is energy dissipation. For example, at 1 velocity will be very higher comparing to velocity at 2. If we allow water to flow over a velocity of 1, velocity at 1 itself, then there will be a huge erosion of soil. Erosion of soil will happen at river bed. So to avoid only we are providing hydraulic jump provision. Okay, so if we allow velocity with v1, then there will be a lot of scoring or erosion occurs in river bed. Okay, at section 2 there will be a huge depth, so there will be velocity will be very minimum, so it will not cause any erosion or abrasion. Okay, so comparing to section 2, at section 1 energy will be maximum. So by producing hydraulic jump we are reducing the energy. Okay, energy of the water. Okay, it's used to dissipate the energy. Then second one is to prevent the scoring of downstream structures. Then third point, it increases the weight on apron. Apron is nothing but a provision which is provided at the exit of dam. Okay. Then next is fifth point, it can be used for mixing the chemical. Okay. Then for increasing the aeration, as I said, sixth point, it's used to aerate the water for city water supplies. Okay. Then we discussed about different type of hydraulic jumps. There will be 6 types of hydraulic jumps. It will be based on its fruit number. Kindly note about this, because if objective questions are asked, then there will be questions, and there will be a lot of questions will come from this fruit number ranges and types of jumps. These are the jumps we discussed in last session. Okay. Now we will go for depth of hydraulic jump derivation. We know it consider section 1. In section 1, depth will be very minimum, but at section 2, after jump, depth will be maximum. Okay, y1 is a depth at section 1, y2 is depth at section 2. What is depth of hydraulic jump means? These depth differences. For example, depth is changing from y1 to y2. Then the depth of hydraulic jump is nothing but is equal to y2 minus y1. Now we will derive how this depth of hydraulic jump is arrived. Okay, we have to know the relationship between y1 and y2, because based on that only we can convert y2 in terms of y1 or y1 in terms of y2. Okay, let's see. Before going to derivation, actually pressure distribution is not hydrostatic. Hydrostatic means we know Pascal law. Okay, Pascal Archimedes principle. If depth increases, there will be increase in pressure. Actually the theory is not applicable for hydraulic jump, because in hydraulic jump pressure distribution will not be hydrostatic. But for deriving and simplification, we are assuming here pressure distribution as hydrostatic. Okay, I am assuming pressure distribution as hydrostatic. That means nothing but linearly varying triangular shape of pressure distribution in water. Okay, at bottom pressure will be gamma times, gamma means unit weight of water, times y1. At section 2, at bottom pressure will be gamma times y2. Okay, now let's see the terms. Q is as we discussed in unit 1 and unit 2 also. Q is nothing but discharge per unit width. I know what is discharge per unit width. Discharge per unit width is nothing but velocity times its depth, v1 into y1. We know discharge remains constant as per continuity equation. Discharge will not vary. Okay, so discharge will be same. So I am applying continuity equation at section 1 and 2. v1 y1 is equal to v2 y2. Then I am taking v1 is equal to small q divided by y1, v2 is equal to small q divided by y2. Then a1 and a2 are cross sections at 1 and 2. p1 and p2, that is nothing but pressure force due to water pressure at 1. p2 is nothing but force due to water pressure at section 2. Then unit weight is taken as gamma. Okay, let's see. Here I am considering section 1. At section 1, I already said, but at bottom pressure will be gamma times y1. Then how I can calculate P1? P1 is nothing but pressure force, that is nothing but area of this pressure distribution diagram. I know it's a triangular shape, so its area is equal to half the times breadth gamma into y1 into depth y1. So P1 is equal to gamma into y1 square divided by 2. Like that, P2 is equal to gamma into y2 square divided by 2. Okay. After that, I am calculating net force between 1 and 2. As I said, there will be a loss in section 1 and 2. So surely that will not be equal. So that will be difference in net force is nothing but P2 minus P1. gamma into y2 square by 2 minus gamma into y1 square by 2. We know y1 value y2 value will be greater than y2, so p2 will be greater than p1. Okay, then during this transition there will be change of velocity is v1 minus v2. I am applying momentum equation. Momentum equation is nothing, we know what is momentum. Momentum is mass of water per second into change in velocity. So mass of water per second is nothing but continuity equation. As per continuity equation, density times q into v1 minus v2. Okay, now I am equating these two terms. If I am equating the net change in force at sections 1 and 2 is sigma p is equal to rate of change of momentum, that is nothing but gamma times q small q times v1 minus v2. If I am equating, I'll get one equation. If I am equating and substituting v1 and v2 in terms of q, then I will get a equation as y2 square plus y1 plus y2 minus 2q square divided by g into y1 is equal to 0. It is almost equal to, it will be in a form of a into x square plus b into x plus c is equal to 0. If I am comparing this, a value will be 1, b value equal to plus y1, c value will be equal to minus 2q square divided by g y1. Then I know for this quadratic equation, solution will be minus b plus or minus root of b square minus 4ac divided by 2 times a. If I am applying that equation then and solve, then I will get final derivation as y2 is equal to minus y1 by 2 plus root of y1 square divided by 4 plus 2v1 square y1 divided by g. Then if I am simplifying v1 y1 everything, I am taking y1 out, then I will get a equation of y2 is equal to final y1 by 2 into root of 1 plus 8 f1. F1 means fruit number at section 1, the square minus 1. It is a very important equation. If exam is a descriptive type, then you may expect this derivation. But if exam is in objective type or if exam is a objective type, then derivation is not that much important. You have to mainly focus and memorize this final formula of y2. This is the relationship between y2 and y1. So y2 is equal to y1 by 2 root of 1 plus 8 f1 1 square minus 1. We may write this also in y2 is equal to y1 by 2 minus 1 plus root of 1 plus 8 fn 1 square also. Okay. Here this is the relationship between y1 and y2. If I am if I know the value of y1, if I know the value of f1, I know what is f1. F1 is nothing but fruit number at section 1. Then I will calculate y2. If I know y1 and fn1, then I will calculate y2. Otherwise, we can write this equation in different form. y1 is equal to y2 by 2 into root of 1 plus 8 f2 the fn to the square minus 1. By using this second equation, if I know y2 and fn2, then I will calculate y1. Or if I know fn1 and y1, then I calculate y2. Okay, either one section of section data at any one section. If I am knowing the data at first section 1, then I can calculate depth at section 2. If I know the section data at section 2, then I can calculate depth at section 1. Okay, so by using that, if I know any one section data, then I can calculate remaining section data also. Okay, by using this only, we are going to solve problems. This is very important derivation. If we are looking for some objective questions, you may surely you will get most number of questions from this derivation. This final equation. Either section 1 data will be given and section 2 data may be asked, or section 2 data may be given and section 1 data will be asked. Like that, vice versa. It can be happen in both ways. Okay, So you have to calculate both section datas. Okay, either one section datas will be given. Based on that, we have to calculate second section data. Okay, this is a depth of hydraulic jump equation. This is called depth of hydraulic jump equation. Okay, now let's discuss about energy loss. As I said, there will be a flow will be changing from supercritical to subcritical. Supercritical to subcritical flow change occurs energy dissipation. Okay, energy dissipation occurs. Okay, this is a very important thing. Then here, if I know y1, if I know y2, then what is depth of hydraulic jump means y2 minus y1. Depth of hydraulic jump is equal to y2 minus y1. Okay, next we will discuss about this. I know what is energy. I know what is head loss. Specific energy at 1 minus specific energy at 2. Okay, I know what is the specific energy equation. Specific energy is nothing but depth of flow plus v square by 2g. So E1 is equal to y1 plus v1 square by 2g. Like that, E2 is equal to y2 plus v2 square by 2g. So head loss will be difference between these two things. Then I know I am substituting velocity in terms of discharge per meter width. Then I will get head loss is equal to final equation as head loss is equal to q square by 2g into y2 minus y1 into y2 plus y1 divided by y1 square y2 square minus y2 minus y1. Then from previous equation I derived as small q square is equal to g into y1 y2 divided by 2 into y1 plus y2. If I am substituting that, then I will get head loss, final head loss is equal to y2 minus y1 the whole cube divided by 4 into y1 y2. For exam point of view or objective questions point of view, final data itself, final equation itself is enough for examinations. Okay, so head loss is equal to y2 minus y1 the whole cube divided by 4 into y1 y2. So far we discussed about two equations. First equation is depth of hydraulic jump. Depth of hydraulic jump is nothing but y1 minus y2. Y2 minus y1. Here formula is given as wrong way. Okay, y2 minus y1 is a correct equation for depth of hydraulic jump. And then for calculating, if I know y1 and fn1, then I can calculate y2 like that. If I know y2 and fn2, then I calculate y1. So by using first section data, I can calculate second section values. Either second section data, I can calculate first section values. Okay. Then I like that I am calculating head loss equation. Here head loss is equal to y2 minus, for head loss calculation both y1 and y2 both should be known. Okay, after that only I can calculate head loss at that section. Okay, so this is the important equations which are used in hydraulic jumps. In third unit, if problems are asked, then these two are the formulas which can be used. Okay, other than these two formulas, there is no other formulas, other mathematical derivations are in third unit. So for third unit, in problem point of view, these two equations are very important. First one is depth of flow equation, depth of hydraulic jump equation. Then second one is head loss in hydraulic jump equation. Okay, in head loss equation, we have to know both y1 and y2. For depth of hydraulic jump equation, data at any one section is enough to calculate data at another section. Then I can calculate hydraulic jump. Okay, for the third unit, if problems are asked, then you have to use these two formulas only. Other than that, there is no other mathematical derivations for unit 3. Okay, now let's discuss about length of jump. Length of jump is nothing but experimentally it found as 5 to 7 times the depth of jump. I know what is depth of jump, y2 minus y1. So length of jump will be is equal to approximately equal to 5 to 7 times y2 minus depth of jump. Okay, these two derivations and this one formula, these three are three equations are which mostly used for calculating problems. Okay, if problems are asked in third unit, then you have to use both these three formulas. Other than this, remaining things are theories only. In next module we will discuss about salinity. Okay, salinity, the term, we will discuss about in next module. Then after that, after discussing about salinity, then we will discuss some problems in hydraulic jumps. Then with that we can conclude the unit 3. Okay, thank you.